You type a sentence. A red fox in a snowy forest, golden light. A few seconds later, there it is. A photograph of a thing that has never existed that nobody drew. Now you might guess the AI works like a painter. Blank canvas, then stroke by stroke it adds the fox, the snow, the light, building the picture up. It does the exact opposite, and the opposite is so strange it is worth slowing all the way down. The AI starts with a canvas of pure random static, the gray snow of a TV tuned to nothing. And then it removes noise. Step by step it asks if this static were secretly a red fox in a snowy forest, what would be hiding underneath, and it nudges the pixels that way. A little less noise, a little more fox, over and over until the static becomes the picture you asked for. It paints by unnoising, and here is the promise of this episode. Once you really see how that one trick works, a whole pile of mysteries, why it is fast, why your exact words matter, why it used to draw hands with 7 fingers, all fall out of the same idea. Let us watch it happen. There are 2 processes here, and only one of them is hard. The easy one we do on purpose. Take a real photo and slowly sprinkle in random noise, a tiny bit at a time over many small steps until nothing is left but static. That is the forward process. It is fixed. It is just adding noise. No intelligence required, you could code it in an afternoon. The whole trick is learning to run that backward. So you show a model millions of pairs, the same image slightly noisier and slightly cleaner, again and again, and it learns one thing. For any noisy image, what does a single small step toward clean look like? That learned step, take me a little nearer to a real image, is the reverse process. And that essentially is the entire model. So to generate something new, you start from fresh static the model has never seen, and apply that learned step again and again. Each step removes a little noise and commits to a little more structure, until a coherent image emerges that was never anywhere in the training data. The idea comes from physics, from how you would reverse a drop of ink diffusing through water, which is exactly why these are called diffusion models. That is the skeleton. The rest of this episode is muscle on the bones, which way is toward a real image, how your words pick which one, and how 2026 made the whole walk take almost a single stride. So pin down the thing we keep waving at. A step toward a real image. Toward what exactly? Here is the picture to hold. Imagine every possible image as a single point in a vast space. Most of that space is garbage, pure noise, smears, nothing. But the images that look real, foxes and faces and forests, are not scattered randomly. They cluster together on a thin surface inside that space. Researchers call it the data manifold. Pure static sits far out in the empty void, nowhere near it. Now at every point in that space, the model has learned to predict one thing. One arrow. The direction that points from where you are toward that surface of real images, toward more plausible, and generating an image is just this. Drop a point in the void, read the arrow, take a small step along it, read the new arrow, step again. You are not erasing noise so much as riding a current home, onto the surface where real images live, and the fox is wherever you happen to land. That is the deep, clean idea, and it is worth saying what it is not. It is not collage. The model is not stitching together scraps of training photos, and it is not looking anything up. There is no database of foxes inside it to retrieve, and it is not subtracting the noise it can see in front of it like a photo filter. It is estimating a direction toward where real images are dense and walking there. A compass, not an eraser and not a scrapbook. Now one honest aside, because it saves you real confusion the moment you read anything about this. If you go look under the hood, you will find people arguing about whether the network predicts the noise or the score or the velocity. 3 different words and they sound like 3 different theories. They are not. They are the same arrow, written in 3 coordinate systems. The noise version says, predict the static I added, and the step toward clean falls right out of it. The score version says, predict the direction in which real images get more likely, which is, word for word, the arrow we just drew. The velocity version says, predict which way and how fast to move along the path from noise to image. Same arrow. You can convert any one into the other two with a line of algebra. So when a paper says it switched from noise prediction to velocity prediction and got better results, do not picture a new idea. Picture the same compass needle relabeled, because one labeling happens to be easier for the math to learn from. And there is a concrete reason which one wins. Predicting the noise is shaky when the image is almost clean, because there is barely any noise left to predict. Predicting the clean image is shaky at the other end, when the input is almost pure static and the model would have to hallucinate a whole picture. The velocity version is the blend that stays well-behaved all the way across, which is exactly why the newest models predict it. One arrow, 3 names. Do not let the jargon fool you into thinking there are 3 machines in there. There is one. Why the arrow even points the right way and why following it from static actually lands on a face is its own beautiful story, and it has the next episode all to itself. Here, just hold the picture. One learned arrow followed home. Good, but everything so far only makes a real image. Some plausible fox. How does your fox, red in snow, in golden light, get chosen out of all of them? 2 pieces. First, your prompt does not go in as raw words. It passes through a text encoder, a model whose only job is to turn your sentence into vectors the image model can use. Those vectors then reach into the denoiser through a mechanism called cross-attention. At every single step, the half-formed image looks back at your prompt and asks, given what I am supposed to be, which way now? The picture is constantly consulting your words. Second, and this is the clever bit, the model does not just nudge toward your prompt. It exaggerates. This is classifier-free guidance. At each step, the model computes the move twice. Once knowing your prompt, once deliberately ignoring it. That is the hidden price. By the way, 2 passes through the network on every single step instead of 1, which roughly doubles the work. And it is why a lot of 2026 research is on getting the same steering for less. The difference between those 2 moves is the part of the step that exists purely because of your words. So it takes that difference and leans into it, harder than either move alone. There is a knob for how hard, the guidance scale. Turn it low and the image drifts off, vaguely foxish. Turn it up and it leans firmly toward your prompt. But in this catches everyone, more is not better. Turn it too high and it overcooks, garish, oversaturated, overliteral, the AI shouting your prompt back at you and losing all variety. There is a sweet spot, not a maximum. And here is a fact that surprised the field. Making the text encoder bigger and better improved prompt following more than making the image generator bigger did. The reader of your words mattered more than the painter. So these encoders climbed a ladder from a modest text model to a large one, to, in some 2026 systems, a full language model bolted on just to understand the prompt. Which is much of why a 2026 model handles a long, fussy sentence so much better than the models of a few years ago. Now a fair objection. The original recipe ran this denoising step many times over, and an image is millions of pixels, and a big neural network is heavy. Doing all of that on every pixel, over and over, should be impossibly slow. So how does this ever run on a laptop in seconds? The breakthrough that put image AI on normal hardware is one move. Do not do the noisy dance on the raw pixels at all. First, compress the image into a small summary, a latent, using a separate little model called a variational autoencoder, a VAE. Think of the VAE as a compressor that has learned which details actually matter. Then do all the denoising, every single step on that small compressed version. And only at the very end decode the finished latent back up to full pixels once. This is latent diffusion. It is, literally, the stable and stable diffusion. To put numbers on it, and these are specific to the original stable diffusion, not a law, a 512 by 512 image became a 64 by 64 latent with a handful of channels. Far less to chew on at every step, which is precisely why it fits on a consumer graphics card. And notice the clean division of labor. The VAE throws away the imperceptible pixel-level detail. The denoiser gets to spend all its effort on the thing that actually matters, the meaning and the composition. Newer models use bigger, richer latents, so do not memorize that 64, but the move is the same. Paint in a small room, enlarge at the end. And the thing doing that denoising in the small room is worth one quick look, because the textbooks are already out of date. For years, the denoiser was a particular shape of network called a UNet, built for images, good at zooming out to grasp the whole scene and back in to fix the details. If you read a tutorial, it will probably still tell you a diffusion model is a UNet. For the frontier, that is no longer true. The newer models swapped it for the same architecture that powers the language models from earlier in this series, the transformer, here called a diffusion transformer. It chops the small latent into a grid of patches, treats them like a sequence of tokens, and lets every patch attend to every other patch, so the model can reason about global layout the way it reasons about a sentence. The latest step folds your words into that same attention. Instead of the prompt poking in from the side, the text tokens and the image patches sit in one shared stream and attend to each other directly, as equals. So the denoiser you should picture in 2026 is not a special image gadget. It is a transformer, the very same family idea, pointed at patches of a picture instead of words. One architecture, quietly eating the whole field. There is one mystery left, and it is the biggest leap of all. If this takes hundreds of denoising steps, how do 2026 models paint almost instantly? It came in two waves. First, smarter math without retraining anything. The original recipe needed something like 1,000 steps. Better solvers, clever ways to take bigger jumps along the same path without falling off. Cut that to a few dozen with almost no loss in quality. To go lower, you change the training itself. Distillation and consistency models teach a fast student to leap across many of the teacher's steps at once, collapsing dozens into a handful, sometimes down to a single step. But the deeper shift, the one that defines the 2026 frontier, is flow matching. Flow matching is the general idea of training the model to follow a chosen path from noise to image, and then picking the easiest path to walk. Pick the straightest possible path, a straight line, and you get the version called rectified flow. Go back to that path from noise to image. In the original diffusion, that path is curved and wiggly, so you have to creep along it in many tiny steps to stay on track. Rectified flow trains the model to make that path straight instead, and a straight line you can cross in one big confident stride. Now, the part that experts are picky about, so let us get it exactly right. Flow matching is not a rival that beats diffusion. They are the same thing. The precise statement is that diffusion is the Gaussian case of flow matching. Flow matching is the more general framework, and classic diffusion is one specific instance of it. Same walk from noise to image, just a cleaner, straighter way to set it up and train. And this is not a research demo, it is shipping. The frontier image models of 2026, the flux and stable diffusion families and their kin, are built on flow matching and generate in a small handful of steps by default, and they're distilled turbo variants in just a few, sometimes a single stride. Fast generation stopped being the hard part. Let us deal with the jokes honestly, because the way they got fixed teaches the whole lecture in reverse. For a couple of years, AI images were infamous for two things: hands with 6 or 7 fingers and gibberish text on signs, menus, t-shirts. Both were real. Both are mostly gone now, and the reasons are the two ideas you already have. Hands were hard because early models learned local pixel patterns, what skin and a knuckle look like up close, with no firm grip on the fact that a hand has exactly 5 fingers. As the models got better, and especially as the denoiser became a transformer that reasons about the whole layout at once, correct hands became routine. Text was garbled because, back then, the model barely read your prompt. It saw text-shaped scribbles in its training images and copied the shape, not the spelling. The fix was the very thing from earlier, a much stronger text encoder that genuinely reads, so a short, clear line of text now comes out legible, where a few years ago it was nonsense. So these were never permanent walls. They were a young technology's growing pains, and watching them get fixed is just watching the mechanism mature. A couple of honest present-day caveats, stated as the exceptions they are. Long, dense paragraphs and tiny labels can still come out garbled, even when a headline renders cleanly. And precise counting and exact spatial relations, the right number of objects, this one strictly to the left of that one, can still slip occasionally, even in 2026. But that line is moving the same direction as all the others fast. And one more thing that is true now and matters. These images are good enough that you often cannot tell. So from August 2026, rules like the European Union's AI Act require AI-generated and manipulated media to be disclosed and machine-readably marked. The technology to fool you and the duty to label it arrive together. We will sit with that responsibility properly when we get to faces and voices. So here is the whole thing in one breath. When you type a prompt and watch an image resolve out of nothing, you are watching a single point of pure static get walked, step by step, along arrows that point toward real and toward matching your words. It happens in a small compressed room for speed. The network steering it is a transformer, and in 2026 it takes just a few strides because the path got straightened. 5 moves. Start from static. Follow the arrow toward real images, the same arrow whether you call it noise, score, or velocity. Let your words tilt that arrow. Do the whole walk in a compressed latent for speed, and straighten the path so it is nearly one stride. That is not magic and it is not a collage. It is a walk and now you can follow it. We took the arrow as given today, the compass that points toward real. Next time we earn it. We open up why that arrow points the right way at all, why nudging static really does land on a face, and why newer models need only a handful of nudges instead of 1,000. No math, just moving geometry. And notice, everything here lives in continuous space, smooth pixels you can nudge a little at a time, which is exactly why diffusion conquered images, while the autoregressive, one token at a time approach you met earlier conquered text. In 2026, even that line is blurring and some image models now generate in tokens too. But that is a story for later. This was painting, a still picture holding still. Soon we make it move.